All right, let's dive in. Today we're going to build a bridge between two worlds that you'd think have nothing to do with each other, the deepest secrets of pure mathematics and the mind-bending reality of quantum physics. We're talking about the Hilbert-Pólya Conjecture.
So, what if I told you that the key to understanding prime numbers, the fundamental building blocks of all arithmetic, isn't buried in some dusty old math book? What if it's actually hidden in the quantum world, in the humming energy levels of an atom? It sounds completely out there, right? Almost like science fiction. But this one idea has kept some of the smartest people on the planet completely obsessed for decades.
Okay, so to get our heads around this absolutely massive idea, we're not going to start with a bunch of crazy equations. No. We're going to start with something much simpler, a little puzzle involving matrices.
So first things first, what the heck is an operator? Well, don't let the name scare you. It's basically just a rule. Think of it like a machine. You put something in one side, say a number or an arrow, and the machine follows its rule and spits out something new on the other side. That's it. Input, rule, output. Simple.
All right, let's build this puzzle together. Step 1. Here's our operator. It's a nice simple 2x2 matrix. Step 2, we're going to let this operator do its thing on a vector. And you can just picture a vector as an arrow pointing in some direction. That's all it is. But here's where it gets really cool. Step 3. It turns out, for this particular operator, there are some very special vectors. When our operator gets a hold of them, it doesn't twist them or change their direction at all, it just stretches them, or maybe shrinks them. And that brings us to step 4. That specific amount of stretch, that magic number, well, that's what we call an eigenvalue.
So, for our little puzzle here, what are these magic stretch factors? What are the eigenvalues? They turn out to be the numbers 1 and 3. And the most important thing to notice right now is that they're just normal, real numbers. No weird fractions, no imaginary stuff, just clean, simple numbers.
And this is the big takeaway. This is the crucial bit. The matrix we picked wasn't random. It was symmetrical. And there's a rock-solid rule in math that says symmetrical operators always, and I mean always, spit out real eigenvalues. No exceptions, just real numbers, okay? Burn that rule into your brain, because it is the key to this entire story.
Okay, you got that rule? Symmetrical operators give real eigenvalues. Now let's take that simple idea from our little puzzle and point it directly at one of the biggest, baddest, most famous unsolved problems in all of mathematics, the Riemann hypothesis.
So, at the very heart of this huge mystery, you have these things called the Riemann zeros. Now, don't worry about the complex math behind them. Just picture them as a secret, never-ending list of special numbers. For more than a century and a half, mathematicians have been like explorers, mapping out these numbers, hunting for some kind of hidden pattern.
And wouldn't you know it, back in the 1800s, a guy named Bernhard Riemann thought he found the pattern. He made this incredibly bold claim that all the important zeros, all the non-trivial ones, lie on one single, perfectly straight line. We call it the critical line. And get this, we've checked trillions of them, and every single one we've ever found is right there on that line. It's an absolutely perfect, almost unbelievable alignment.
But here's the catch, right? Checking trillions is amazing, but it's not the same as checking all of them, because there are infinitely many. So for over 160 years, with some of the most powerful minds and computers working on it, why can't we prove it? Why can't anyone show for sure that not a single one of these zeros ever wanders off that line?
And this is where it all comes together. This is where our simple puzzle smashes right into that grand mathematical mystery. This is the physics connection.
Okay, so let's put these two ideas up side by side. In one corner, you have our simple puzzle. We had a symmetrical operator, and what did it give us? Real eigenvalues, the numbers 1 and 3. In the other corner, you have the Riemann hypothesis. We have this mysterious list of zeros, numbers like 14.13, 21.02, and on and on. And now for the big question, the heart of the conjecture. What if these Riemann zeros are really just the eigenvalues of some other, much more complex operator, an operator from the world of quantum physics?
And that, my friends, is the Hilbert-Pólya Conjecture. It's this absolutely mind-blowing idea that the Riemann zeros aren't just some abstract mathematical curiosity. No, they are the actual eigenvalues, those stretch factors we talked about, of some physical quantum operator that we just haven't been able to find yet.
And this is so much more than just a cool what-if idea. It's a roadmap. It's a potential pathway to finally proving the Riemann hypothesis once and for all.
So here's the game plan. It's a 4-step recipe for a proof.
Step 1, you have to actually find this mystery quantum operator. That's the hard part, obviously. Step 2, you have to prove that this operator is self-adjoint. That's just the fancy physics way of saying it has that special kind of symmetry we talked about. Now, remember our golden rule? A symmetrical or self-adjoint operator has to have real eigenvalues. And here is the punchline. The conjecture says the heights of the Riemann zeros on that critical line are the eigenvalues. So if you can prove the operator is self-adjoint, you automatically prove that all its eigenvalues, all those heights, have to be real numbers. And that forces every single zero to lie exactly on that critical line. Boom! Step 4, the Riemann hypothesis is solved. It becomes a consequence of physics.
I mean, just stop and think about what this means physically. It's staggering. It suggests that these numbers, which are intimately tied to the distribution of prime numbers, the most fundamental things in math, could actually be the specific, measurable energy levels of some physical quantum system. That's like discovering that the notes of a piano are determined by the orbits of the planets. It's a connection that just shouldn't exist, but it might.
So where are we now? How's the search for this magical operator going?
Well, let's be real. The conjecture is still just a conjecture. It's unproven. And the main reason is that nobody has found the operator. It's still out there somewhere, like a holy grail for mathematicians and physicists, but there are these incredible, tantalizing clues that suggest they're on the right track.
And maybe the biggest hint of all, the one that really gives people chills, is a statistical one. If you look at the spacing between the Riemann zeros, the gaps between them, that pattern of spacing is a statistical dead ringer for the spacing between energy levels in chaotic quantum systems. Now, that's not a proof, not even close, but as far as circumstantial evidence goes, it's about as good as it gets. It screams that there's a real connection here.
So at the end of the day, we're left with this absolutely profound question. It feels like the prime numbers dance to a kind of music, a secret harmony that's described by these Riemann zeros. And if the Hilbert-Pólya conjecture is right, then we're forced to ask, what undiscovered quantum system humming away somewhere in the universe is composing the music of the primes?